In this tutorial, we're going to talk about oxidation numbers. These are sometimes called oxidation states. Oxidation numbers are a really useful way to help keep track of electrons in compounds and reactions, and in particular redox reactions. Where atoms are losing electrons or gaining electrons, it's really good to know what's being oxidized, what's being reduced, how many electrons are flowing. But it's also an interesting concept for other parts of chemistry where we want to know how many electrons an atom might have. Now, the oxidation number for an atom is the positive or negative charge that atom would have if the compound were completely ionic. So even if the molecule is covalently bonded, the oxidation number is the charge it would have if it were completely ionic. This puts everything on the same footing. For example, magnesium oxide, MgO, is ionic. It contains O2-, and we think of the oxygen as having a bonding power or valency of 2, and we give it an oxidation number of -2. H2O is a covalent molecule, perhaps very different, but in many ways very similar. It's covalent with 2 OH bonds, and the oxygen again makes 2 bonds, has a valency of 2, and we give it an oxidation number of -2, just to show the link between oxygen's valency in these two systems. Now, there's a set of rules for assigning oxidation numbers, which we're going to go through. They're pretty straightforward, but the most important thing is to use them in order. Don't jump from number 1 to number 7 and back again. Go through 1, 2, 3 in order. So the first rule is that an atom in an elemental form, a lump of iron, chlorine gas, graphite, has an oxidation number of 0. In a molecule or a compound, the sum of the oxidation numbers is equal to 0. But if we've got a cation, the sum of the oxidation numbers of the atoms is equal to the positive sign of the cation. If we've got an anion, the sum of the oxidation numbers of all the atoms is equal to that negative charge for the anion. Given that, we ascribe the most electronegative element, fluorine, to have an oxidation number of -1. But we just need to remember that we've got to apply rule 1, 2 and 3 first. For example, in F2, where it's in its elemental form, its oxidation number is 0. The alkali metals, the group 1 metals, have an oxidation number of +1, except again if they're in the metal, like a lump of sodium, where the atoms would have an oxidation number of 0, rule back to rule 1. And the alkaline earths, the next most electropositive, are given an oxidation number of +2, except again in the metals, where those group 2 elements would have an oxidation number of 0. And so we go on. So we've done fluorine, we've done the most electronegative atom, we've done the most electropositive metals, groups 1 and 2. So the next one to look at is oxygen. The oxidation number of oxygen is given as a -2, except if it's in a peroxide or in the elemental forms that we talked about before. In a peroxide like hydrogen peroxide H2O2, the oxidation number is -1. But also, if that oxygen is bonded to fluorine, then the fluorine from rule 4 will have a -1. And so the oxygen is there to balance out the charge of the fluorine. For example, in OF2, we've got 2 fluorines, so 2 -1s, then the oxygen must be +2 to make sure that the whole molecule has an overall charge of 0. The halogens are normally -1, except as we'll see in just a second, that can be overridden if we are bonding to fluorine. And then lastly, the oxidation number of hydrogen is +1 when bonded to a non-metal and -1 when bonded to a metal. Let's do some examples. Our first one, ClF3 molecule. It's a molecule with no overall charge, so the sum of the oxidation numbers has to equal 0. We've got 3 fluorines, each fluorine is -1, so the oxidation number of the chlorine must be there to balance out the charges of the fluorines. 3 -1s, the chlorine must have a charge of +3. +3 from the chlorine, 3 lots of -1 from the fluorines gives us a total of 0. The overall charge of the molecule is 0. Let's do a cation, ClF4+. We have an overall +1 charge, so the sum of our oxidation states has to equal to +1. Fluorine, -1, and there's 4 of them. So we've got 4 -1s from the fluorine, an overall charge of +1. The chlorine must be oxidation number +5. +5 from the chlorine, 4 lots of -1 from the fluorines, added together gives us the +1 charge of our cation. Having done a cation, let's do an anion, ClF4-, so we've got a -1 charge overall. 4 fluorines, each -1, So this time, in order to make everything add up to -1, the chlorine must have an oxidation number of +3. +3 from the chlorine, 4 lots of -1 from the fluorine, gives us a -1 charge overall. Okay, now in transition metal chemistry, it's really quite difficult to name or work out what compound it is, because the transition metal can have a number of different oxidation numbers and form a number of different compounds. For example, chromium forms more than one oxide. CrO3, the compound has no overall charge. We can work out the oxidation number of the chromium because we know that the oxygens are going to be -2. There's 3 of them, each one's -2 is -6, so the chromium must be +6 so that the overall charge is 0. +6 on the chromium, 3 lots of -2 on the oxygens gives us that 0 overall charge for our compound. But here's a different oxide of chromium, Cr2O3. Again, no overall charge. This time we've got 3 oxygens, each one -2. So the 2 chromiums must give us +6, each chromium must be +3. 2 lots of chromiums, 2 lots of +3, balancing 3 oxygens to 3 lots of -2 to give us an overall charge of 0. We could also have chromium and oxygen in a complex with an anionic charge like this one, Cr2O7 2-, dichromate. Same rules as before, the iron has an overall charge of -2, oxygen has an oxidation number of -2, the 2 chromiums must be balancing all this out. We've got 7 oxygens, each one -2 is -14. We want to end up with -2, so that each chromium must be +6. 2 lots of +6 is +12. 7 lots of -2 is -14. +12 -14 gives us that overall charge of -2. Okay, lastly, let's do some examples from nitrogen chemistry. Nitrogen is well known for forming lots of different oxidation numbers. Nitric acid we'll start with. We've got 3 lots of oxygen, 3 lots of -2. We've got a hydrogen, +1. So in order to make the whole thing have an overall charge of 0, the nitrogen must be +5. +1 from the hydrogen, +5 from the nitrogen, and -6 from the oxygens adds up to 0. Nitrate, NO3-. Now the charges are going to add up to -1 because it's an anion. 3 lots of oxygen, 3 times -2 is -6. The nitrogen must again be +5. +5 on the nitrogen, -6 from the oxygens gives us an overall charge of -1. NO2, 2 lots of -2 from the oxygens is -4, and the nitrogen must be +4. Nitrous acid, HNO2, 2 oxygens is 2 times -2 is -4. 1 hydrogen +1. What must be the charge of the nitrogen be to balance the whole thing out? It must be +3. +1 on the hydrogen, +3 on the nitrogen, -4 from the oxygens gives us our total of 0. The molecule has no charge. NO2-, minus charge overall. 2 lots of -2 from the oxygens is -4. The nitrogen must be again +3. +3 from the nitrogen, -4 from the oxygens, adds together to give us -1, which is the charge on the iron, NO2-. NO, -2 on the oxygen, +2 on the nitrogen. N2O, -2 on the oxygen. There's 2 nitrogens, each one must be +1. 2 lots of +1 and a -2 gives us a total of 0. N2 itself, well, it's an element, elemental form of nitrogen, and so it's a 0. NH2OH, we've got 1 oxygen -2. We've got 3 hydrogens in total. 3 lots of +1 is +3. No overall charge, the nitrogen must be -1. +3 from the hydrogens, -1 from the nitrogen, -2 from the oxygen adds up to give us a 0. Hydrazine, N2H4, 4 lots of hydrogens, 4 lots of +1, +4. Nitrogen must be -2. The +4 from the hydrogens is balanced by 2 lots of -2 from the nitrogens. And lastly, ammonia, 3 lots of +1 from the hydrogens must be balanced by -3 on the nitrogen to give us an overall charge of 0. +3 from the hydrogens, -3 from the nitrogens gives us 0 for the overall molecule. And as you see, Nitrogen can go all the way from +5 down to -5, and every step in between. Nitrogen has an intermediate electronegativity, it has an odd number of valence electrons, and as a result, nitrogen has one of the widest range of oxidation numbers throughout chemistry.